Ever wondered how crucial the Standard Template Library or STL is in C++ programming? Well, it's a fundamental component that provides a rich set of tools, enabling developers to write efficient and reusable code. Introduced in C++ 98, STL has been expanded and refined over the years, becoming an integral part of modern C++ programming. At the heart of STL are three key components: containers, algorithms, and iterators. Containers are versatile classes designed to store collections of objects. These containers come in a variety of types like sequence containers, associative containers, and container adapters. Then we have algorithms, which are template functions that can be applied to different container types, offering functionalities like sorting, searching, and modifying sequences. Lastly, we have iterators, acting as pointers to elements within a container, supporting operations such as dereferencing, incrementing, and decrementing. Join us as we delve into the intricacies of the STL and how it revolutionizes the way we code in C++. Let's kick off with containers, the heart of the STL. The Standard Template Library, or STL, provides various container classes for storing collections of objects. Think of these containers as the treasure chests of STL, each one specialized to store and manage data in its unique way. First, we have sequence containers. These containers store elements in a linear sequence, much like a line of people waiting for a bus. Examples of sequence containers are vectors, decors, lists, and arrays. For instance, a vector is like a dynamic array. It can grow and shrink in size as needed, making it quite versatile. Next, we have associative containers. These are like smart librarians, as they automatically sort the elements as they are inserted. This makes searching for elements faster. Set, map, multiset, and multimap are common associative containers. Then come the unordered associative containers. These are the rebels of the STL world, as they don't sort the elements. Instead, they use hash functions for quick access to individual elements. Unordered underscore set, unordered underscore map, unordered underscore multiset, and unordered underscore multimap are examples of these types of containers. Lastly, we have container adapters. These are not standalone containers but provide a different interface to sequence containers. It's like putting a new cover on an old book. The content is the same, but the presentation is different. The stack, queue, and priority underscore queue are examples of container adapters. Each of these containers comes with its strengths and trade-offs, and the choice of container depends on the specific requirements of your program. For example, if you need to store elements in a specific order, an associative container like a set would be a good choice. On the other hand, if you need to quickly access individual elements, an unordered associative container like an unordered underscore map might be more suitable. So these are the containers that STL provides for storing collections of objects. Each has a unique role in making your C++ programming tasks more efficient and manageable. So don't be afraid to dive in and explore these treasure chests of the STL world. Now that we've covered containers, it's time to explore the algorithms that STL provides. The Standard Template Library is brimming with a wide range of algorithms. These are implemented as template functions, making them adaptable to different container types. Let's talk about some of these algorithms. First up, we have sorting algorithms. STL provides sort and stable underscore sort for this purpose. Sort rearranges elements in a container in a specific order, while stable underscore sort does the same, but maintains the relative order of equivalent elements. Next are searching algorithms. Find and binary underscore search are two examples. Find locates the first occurrence of a specific value in a container, whereas binary underscore search determines if an element exists in a sorted container, doing so in logarithmic time complexity. STL also includes algorithms for modifying sequences, such as copy, reverse, and rotate. Copy duplicates elements from one container to another. Reverse inverts the order of elements in a container, and rotate shifts elements in a range to the left or right. Numeric operations are another category of algorithms. Accumulate, inner underscore product, and a partial underscore sum are some examples. Accumulate computes the sum of a range of elements. Inner underscore product calculates the inner product of two ranges of elements, and partial underscore sum generates a sequence of partial sums of a range of elements. Lastly, we have set operations like set underscore union, set underscore intersection, and set underscore difference. These algorithms perform operations on sorted ranges as if they were mathematical sets. Set_union forms a new range that includes all unique elements from two ranges. Set_intersection creates a range of common elements from two ranges, and set_difference generates a range of elements that are in the first range but not in the second. These algorithms provided by STL make operations on containers a breeze. They abstract away the low-level details, allowing us to focus on the high-level logic of our code. Whether it's sorting, searching, modifying, or performing mathematical operations, the STL's algorithms have got us covered. They're handy tools that make our coding journey smoother and our code more efficient. Next in line, we have iterators, the glue that binds containers and algorithms together. In the realm of the standard template library, iterators play a pivotal role. They function as the conduit between containers and algorithms, allowing for seamless interaction between the two. But what exactly are iterators? They are objects that behave like pointers, providing a means to access the elements stored in containers, one at a time. Let's delve into the different types of iterators STL offers. First, we have input iterators. These are read-only iterators that allow you to access and read the elements of a container. They're like a one-way ticket. You can only move forward, one step at a time. An example of this is the isStream_iterator that reads from input streams. Then there are output iterators. They're the flip side of the input iterators. They provide write-only access to a container's elements. Again, it's a one-way journey, but this time you're writing or modifying the elements. OStream_iterator is a case in point, writing into output streams. Forward iterators are up next. These are an upgrade to input iterators, providing both read and write access. They still move only in a forward direction, but they give you the flexibility to modify elements while traversing. Bidirectional iterators take it a step further. They offer the same read and write access as forward iterators, but with the added advantage of moving both forwards and backwards. This means you can loop through your elements in either direction. A doubly linked list, for example, uses bidirectional iterators. Lastly, we have random access iterators. These are the all-inclusive package, providing the most flexibility. They offer read and write access, can move forwards and backwards, and even allow you to jump directly to any element, much like an array index. Vectors and dequis typically use random access iterators. Iterators offer a uniform interface for traversing elements, making them an integral part of the STL. By understanding iterators, we gain a powerful tool to leverage the full potential of the standard template library in our C++ programming endeavors. Just like any other tool, STL has its pros and cons. Let's start with the brighter side, the advantages. Firstly, we have reusability. The STL provides a rich collection of generic algorithms and containers that can be easily reused in different projects and contexts. This means you don't need to reinvent the wheel each time you need a data structure or algorithm. Next up, we have efficiency. The designers of the STL took great care to optimize the performance of its algorithms and containers. This results in code that executes efficiently, which is always a plus in the world of programming. Then comes standardization. Being a part of the C++ standard library, the STL ensures portability and compatibility across different platforms and implementations, so you can be confident that your STL-based code will work consistently, regardless of the environment it's running in. Abstraction is another significant advantage. The STL abstracts away low-level implementation details, allowing you to focus on high-level algorithmic concepts and design. This can make your code cleaner and easier to understand. Finally, we have safety. STL containers and algorithms are designed to be type-safe and memory-safe. This reduces the risk of errors and vulnerabilities in your code, making STL a safer choice for development. But of course, no tool is perfect. The STL is no exception, and it has its share of disadvantages. For starters, there's the learning curve. Understanding the STL requires grasping various concepts such as iterators, algorithms, and container types. This can be challenging for beginners. Then we have template errors. Template-based programming in STL can sometimes lead to cryptic error messages during compilation. This can make debugging more difficult than it needs to be. Lastly, we have complexity. Some STL algorithms and containers come with complex time and space complexity guarantees. These require careful consideration when choosing the right tool for a given problem. Despite its challenges, STL remains a powerful tool for C++ developers. It provides a solid foundation for writing efficient, maintainable, and portable code. Just remember, like with any tool, the key is to use it wisely. So, we've taken a fascinating journey through the world of STL. We have explored how the standard template library, a cornerstone of modern C++ programming, offers a rich collection of generic algorithms and data structures. We've delved into the various containers it provides, from sequence and associative to unordered associative containers and container adapters. We've discovered its plethora of algorithms for sorting, searching, modifying sequences, numeric operations, and set operations. We've also learned about the different types of iterators that provide a uniform interface for traversing elements in a container. We've weighed the advantages of reusability, efficiency, standardization, abstraction, and safety against the challenges of a steep learning curve, cryptic template errors, and complex time and space complexities. Despite these challenges, we have seen that the benefits far outweigh the drawbacks. With its rich set of tools, the STL provides a solid foundation for writing efficient, maintainable, and portable code in C++.